welcome back. So, in the last lecture we have solved a few problems, numerical problems rather, on earth pressure theory. So, today we will be taking a couple of numerical problems on earth pressure theory, and then we will be moving to the numerical problems for stress distribution in soil. So, first problem we will take today. The problem says a 5-meter high masonry retaining structure wall has to retain a backfill of sandy soil having a unit weight of 18.2 kilonewton per meter cube and an angle of internal friction of 32 degree. The surface of the backfill is inclined at an angle of 10 degree to the horizontal. Determine the magnitude and point of application of the active thrust on the wall. Okay. So, this is the problem. The problem says that a 5-meter high masonry retaining wall has to retain a backfill of sandy soil having a unit weight of 18.2 kilonewton per meter cube and an angle of internal friction of 32 degree. The surface of the backfill, that is the top surface of the backfill, is inclined at an angle of 10 degree to the horizontal. Determine the magnitude and point of application of the active thrust on the wall. So, this is a kind of inclined backfill problem. Okay. So, and you know, so solution. So, first we will try to find out coefficient of active earth pressure, say Ka, that is nothing but, you know, already we have seen this formulation in the lecture, cos beta into cos beta minus cos square beta minus cos square phi divided by cos beta plus cos square beta minus cos square phi, where beta is the angle of inclination of the backfill and phi is the angle of internal friction of soil, right. So, in this formula if we put, instead of cos beta I can put cos 10 degree into cos 10 degree minus cos square 10 degree minus cos square 32 degree divided by cos 10 degree plus cos square 10 degree minus cos square 32 degree. So, that gives me 0.296. That is the only tricky part of this problem, otherwise this problem is pretty straightforward. So, you can find out the distribution of the pressure, active earth pressure, and from there you can find out the active thrust. Anyway, so this is your active earth pressure coefficient for this inclined backfill. Now, we are going to find out the resultant thrust as asked in the problem. So, the resultant thrust therefore, the resultant thrust PA is equal to half into gamma into Ka into H square, right. So, the formula will be remaining same, only thing is that Ka expression will be different, right. So, here if you put the values, half, gamma is 18.2, K is 0.296 and H is the total height of the retaining wall is 5 meter. So, this gives me 67.34 kilonewton per meter, and this thrust is inclined. This thrust is inclined at 10 degree to the horizontal. That is acts parallel to the ground surface and is applied at a height of what 5 by 3, right. So, that will be the triangular distribution again. So, 5 by 3, that is equal to 1.67 meter above the base of the wall. So, this is your whole problem. Okay. So, you have got the resultant thrust equal to 67.34, which will be inclined, right, which will be inclined at an angle 10 degree with the horizontal, that means parallel to the inclined back face. Okay. Already we have seen this thing when we talked about this inclined back face problem, right. So, it will be inclined at an angle 10 degree with the horizontal and is applied at a height of 5 by 3, because this is a triangular, this will be the triangular distribution. So, 1.67 meter above the base of the wall. So, we will take the next problem. So, next problem says a retaining wall of 5 meter height has to retain a stratified backfill as shown. Find out the magnitude of total active thrust on the wall and locate its point of application. Okay. So, let me draw the wall. So, this is point A, B, C and D. So, you have 3 different stratum. Okay. Depth of top stratum is 1.9 meter, then second layer is 1 meter and third layer is 1.6 meter. And this is your sandy silt, which will be having gamma equal to 18.5 kilonewton per meter cube, C equal to 10 kilonewton per meter square and phi equal to 20 degree. And second stratum is loose sand, which has gamma equal to 17.2 kilonewton per meter cube and phi equal to 30 degree. And third is your dense sand, which has gamma equal to 18.8 kilonewton per meter cube and phi equal to 36 degree. Okay. So, this is the problem. The problem says a retaining wall of 5 meter height has to retain a stratified backfill as shown. Find out the magnitude of total active thrust on the wall and locate its point of application. Now, if you see this problem is little bit different than the problems whatever we solved in the earlier classes. Now, here actually the top layer is having the cohesion. Instead of earlier whatever problem we solved the problems where all the layers will be having cohesionless soil. Now, you have cohesion in the top layer. So, you have to consider that thing. That means, you may have the possibility of getting tension cracks at the top layer, right, as well as you will be getting some tension at the top of the wall. So, that thing you need to consider in the pressure diagram and in the active thrust total active thrust calculation. Okay. So, let us see how we can solve this. So, solution. Now, first one is sandy silt layer. Okay. So, we calculate n phi because we need to know n phi and root over n phi that is there in the equation that you know that. So, tan square 45 degree plus 20 by 2 degree, which gives me 2.04 and subsequently root over n phi is 1.438. So, these things we can calculate beforehand before going to the actual analysis. Okay. So, therefore, PA, that means active earth pressure at point A, okay, that means at the top of the wall. So, what is the magnitude of PA? PA is how do you know that? So, you know that gamma z by n phi minus 2c by root over n phi, that is the actual expression, right. So, in case of cohesionless soil, P is gamma z by n phi minus 2c by root over n phi. So, this is the expression, right. Already you have seen this equation several times in the numerical problems, so whatever we have solved in the last classes. Okay. So, PA in this equation, when we are considering point A, at that time z equal to 0, that means at the top of the wall. So, it will be simply 2c by root over n phi. If you put the values, minus 2 into c is 10 kilonewton per meter square divided by 1.438 is equal to minus 13.9 kilonewton per meter square. Okay. Then this top layer is spanning from point A to point B. So, I will get PB, that is active earth pressure at point B when you are considering stratum 1, that means at the interface, right. So, PB is equal to gamma j by n phi minus 2c root over n phi, which is equal to 18.5 into what is z? Z is 1.9 meter, 1.9 divided by n phi is 2.04 minus 2 into 10 divided by 1.438. So, that gives me 3.3 kilonewton per meter square. Okay. So, we have got the active earth pressure at point A and active earth pressure at point B, as long as we are considering stratum 1. Now, because you have the cohesion in the top layer, so you may expect the tension crack. So, that zone of tension crack is nothing but that will be defined by the depth z naught, right. So, we need to calculate z naught. So, z naught will be equal to 2c by gamma into root over n phi, which is equal to 2 into 10 into 1.438 divided by 18.5, it gives me 1.55 meter. So, we can draw the active earth pressure distribution plot. Let us see how it will look like. So, suppose this is your whole wall, okay. This is your point A, say this is your point B, this is your point C, and this is your say point D. Okay. So, as given, it is 1.9 meter, it is 1 meter, it is 1.6 meter. Okay. So, at point A, what active pressure you have got? Minus 13.9. So, it will be on this side minus 13. I am not writing kilonewton per meter square everywhere, so it will be quite understood. Okay. Then where it is crossing over, where your pressure is becoming 0, active earth pressure is coming from negative side to positive side. Where it is becoming 0? At z naught, right. So, z naught is the distance or the depth at which your active earth pressure is becoming simply 0. So, that is a this point, say this is your 1.55 meter and this is your 0.35 meter. Okay. So, you are getting the distribution like this, okay, where this is your 3.3 kilonewton per meter square, that is active earth pressure at point B. Now, we will consider stratum 2, that is your loose sand, and we will try to find out the pressure distribution. So, second one is loose sand layer. Okay. So, there basically your Ka2 can be defined as 1 minus sine 30 degree by 1 plus sine 30 degree, which comes as 0.33. Okay. Equivalent surcharge intensity, because now your stratum 1 will be acting as equivalent surcharge, right, uniform surcharge on top of layer 2, right. So, surcharge intensity, say Q1 is equal to 18.5, that is your gamma of the top layer multiplied by the depth of top layer, that is 1.9, it comes as 35.1 kilonewton per meter square. Okay. So, therefore, PB, that means active earth pressure at B, as far as you are considering layer 2, that is starting from point B to point C. So, when you are in stratum 2, at that time what is the active earth pressure at point B, and that will give you the discontinuity, that is a jump, right. PB is equal to simply Ka2 into Q1, right. So, that gives me 0.33 into 35.1 is equal to 11.7. So, you will be getting some increase, and that is your 11.7, that is the jump, right, at point B. Okay. So, similarly I can calculate PC, that means active earth pressure at point C, which is the interface, which is eventually or evidently the interface between stratum 2 and stratum 3, right. So, PC is equal to Ka2 Q1 plus Ka2 gamma 2 H2, which gives me Ka2 Q1 is nothing but 11.7 plus Ka2 is 0.33, gamma 2 is 17.2, and what is H2, that is the depth of second layer, is simply 1 meter. So, that gives me PC is equal to 11.7 plus 5.7 is equal to 17.4 kilonewton per meter square. Okay. So, therefore, we can complete here. Now, this point we know. So, from there, so this is your 5.7, this is your 5.7. Okay. So, I have got the pressure up to point C, that means we have covered stratum 1 and stratum 2. Now, we are going to stratum 3. So, stratum 3 is nothing but dense sand layer. Okay. So, there your Ka3 is equal to 1 minus sine 36 degree by 1 plus sine 36 degree, that comes as 0.26. So, equivalent surcharge intensity Q2 is equal to what, 18.5 into 1.9, that is for top layer, plus for second layer 17.2 into 1, that gives me 52.3 kilonewton per meter square. Okay. So, I have got the equivalent surcharge intensity. Now, when basically your top two layers, first layer and second layer, will be acting as surcharge on top of third layer. Okay. So, therefore, I can calculate PC. How I calculate PC? PC is simply Ka3 into Q2. So, Ka3 you know 0.26 and Q2 you know 52.3. So, if you put those values, you will be getting 13.6 kilonewton per meter square. Okay. So, similarly, I can find out PD, that is the active earth pressure at point D, that is the bottommost point of the wall. PD is equal to Ka3 Q2 plus Ka3 gamma 3 into H3. So, that is nothing but 13.6 plus Ka3 is 0.26, gamma 3 is 18.8 and H3 is 1.6. That gives me 13.6 plus 7.8 and total is 21.4 kilonewton per meter square. So, therefore, I can complete the figure now. So, this is 5.7. Now, if you see PC from stratum 3, you are getting PC equal to 13.6. So, that means 11.7 plus 5.7, that was equal to 17.4. From here to here it was 17.4, but when you are considering stratum 3, at that time you have to come back to 13.6. So, basically you are coming back, this is your 13.6 and then so this is your 13.6 from this point to this point and this point is 7.8. Okay. So, this is your pressure distribution, this is the active pressure distribution on the wall. So, now what are the different forces? Because tension crack is happening, so we will be neglecting the tension zone. So, we are not considering the tension zone. So, we will be considering from the point 0 to the positive pressure, right. So, P1 is acting here, okay. P2 is here, which is nothing but this the area under this rectangle, then P3 area under this triangle again, P4 area under this rectangle and P5 area under this triangle. Now, we are going to find out all these forces. So, how we can find out all these forces? So, these forces will be nothing but the area under the respective area curves. Okay. So, suppose I want to calculate P1. How I will calculate P1? P1 is equal to area of this small triangle, right. So, P1 is nothing but 0.5 into 0.35, that is the height multiplied by 3.3, which comes as 0.6 kilonewton per meter run of the wall, and it acts at a point, okay, which is y1 distance above the base of the wall. So, y1 is equal to 2.6 plus 0.35 by 3 is equal to 2.72 meter. Okay. Similarly, you can calculate P2. P2 is equal to 1 into 11.7. So, that is this is the area. So, 11.7 is this and 1 is the depth. So, 1 into 11.7, that comes as, okay. Similarly, you can calculate P2. P2 is equal to 1 into 11.7. So, that is this is the area. So, 11.7 is this and 1 is the depth. So, 1 into 11.7, that comes as 11.7 kilonewton per meter run, and y2 is equal to 1.6 plus 1 by 2, okay, because that will be acting at the mid depth of this rectangle. So, that comes as 2.10 meter. Then P3 is equal to 0.5 into 1 into 5.7, which is equal to 2.9, and Y3 is equal to 1.6 by 1 by 3 is equal to 1.93 meter. Similarly, P4 is equal to 1.6, that is the area under this triangle, okay, not triangle, this rectangle, sorry, this rectangle. So, 1.6 into 13.6, that comes as 21.8, and Y4 is equal to 1 by 6 by 2, that is nothing but 0.8 meter. And finally, P5 is equal to the area under this last triangle, 0.5 into 1.6 into 7.8 is equal to 6.2 kilonewton per meter run, and Y5 equal to 1.6 by 3 is equal to 0.53 meter. So, we have got all the forces and we have got all the locations of or the point of application of each force, right. So, I can calculate the total thrust Pa is nothing but summation of Pi, I is equal to 1 to n, which gives me 43.2 kilonewton per meter run. That means P1 plus P2 plus P3 plus P4 plus P5, okay. And Y bar, that is nothing but summation I is equal to 1 to n Pi Yi divided by summation Pi I is equal to 1 to n, which gives me 52.5 by 43.2, that is nothing but 1.216 meter from base of the wall. Okay. So, I hope that you have understood. So, the main tricky thing is that to get the pressure distribution plot. So, once you get this pressure distribution plot, the rest of the things will be pretty simple. Okay? I mean pretty say mechanics oriented, that means you will be calculating the forces, calculating the center of gravity, and then find out the total thrust and point of application of the total thrust. Okay? So, now with this basically I will conclude the numerical problems for earth pressure theory. Now, we will be solving or we will be taking few numerical problems on stress distribution in soil. So, the problem on stress distribution, find the stress beneath the center that is point O and corner of say figure 1, which I will be showing now for the following data. What are the following data? That is, the area is B by B, which is nothing but 2 meter by 2 meter, and total load on that area capital Q is 800 kilonewton, okay, and the depth at corner, that is Z equal to 2 meter, that means at depth z equal to 2 meter you need to calculate the stress, right, and at center z equal to 2 meter, and the area looks like this. This is your figure 1, square area A, B, C, D, E, O prime. Okay. So, this is the area. Now, on this area is 2 meter by 2 meter, 2 meter by 2 meter. Okay. So, on this area, on this square area, basically your total load is acting as 800 kilonewton, that is the concentrated load, say, force. Okay. Now, you need to find out the stress beneath the center. Center means beneath the point O, at which depth? At depth z equal to 2 meter. So, at 2 meter depth, just below the center you need to calculate the stress by using the formula, okay, by using the concept whatever you have learned so far, and you need to find out the stress beneath the corner. Beneath the corner means at any corner you consider, beneath the corner also at which depth? Same depth, the depth equal to 2 meter. Okay. So, let us solve this problem. So, square loaded area is equal to O prime E B D for point O, and we know, if you recall whatever we have learned in the lecture class, basically any rectangular area you consider, you have the formula, that is sigma V equal to, or the Q V equal to Q naught into I sigma, and this I sigma when you are calculating, that will give you the stress at the corner of any rectangular area. So, if you consider the midpoint or the center of this square area, basically this point should belong to some corner of the rectangle or square, then only you will be able to use that formula, right. Similarly, this corner is fine. So, you need to find out the stress just below the corner of this square area. So, the whole square area, if you consider this is the corner, it is fine. So, you can use the formula directly, but when we are talking about the center of the square, at that time you will not be able to use the formula directly. So, you have to make the whole area, or you have to discretize the whole area in such a way that O will be coming as one of the corner of that loaded area. Okay. So, that we are making. So, total square loaded area is O prime E B D, that is the total square area. Now, for point O, now if I consider point O, for point O basically what we can use? Use 4 times of OABC. What is O? OABC. So, we are discretizing the whole square area in 4 different square areas, and once we consider area OABC, so O is coming as the corner of this area. So, I can find out the stress coming just below point O, because that point is now belong to the corner of this square area, right. So, now this corner, this point will be having the participation of all 4 different squares, right. So, what are the 4 different squares? OABC, OAE, and if you say this one is your F, so OAEF, OF, O prime some point this, and OCD. So, this point is says G, so OCDG, right. So, these 4 things, and you can use the method of superposition. So, each part will be giving you some stress at this point, and the 4 times of this area will be the stress at point O, because point O is not the corner point in the actual problem, in the actual area. So, we have made the point O in such a way that it is coming as the corner of one of the square, small square, right. So, for point O, use 4 times into OABC. So, you consider area OABC, you find out the stress just below point O, that you can find out by using the formula, and 4 times of that will be the total stress at the point O, right. Similarly, for point O prime, O prime is not a problem, O prime is the corner point of the actual area. So, point O prime, use O prime E B D. Okay. So, as per Boussinesq, first one is for the corner at z equal to 2 meter. What is the magnitude of m? M is what? M is b by z. So, what is the value of b? Both b and l both are same in this problem, right, b equal to 2 meter and l equal to 2 meter, because this is a square area. Now, m is b by z. So, 2 by 2, b is 2 meter and z, the depth at which you are interested to find out the stress, that is also 2 meter. So, that is giving me m equal to 1. What is the value of n? L by z, right. So, that is also 2 by 2, that is also 1, is not it. So, you have got m and n. So, once you know m and n from the table whatever I have given in the lecture. So, from that table you can find out I sigma. So, from table I sigma you can find out. So, you can check it, that comes as 0.175. So, if you are not getting I sigma directly, you need to do the linear interpolation. Okay. So, your QV is equal to Q naught I sigma, which is, what is Q naught? Total load is acting as 800 kilonewton, okay, on what area? On 2 meter by 2 meter square area. So, Q naught is nothing but 800 by 4, 2 into 2, okay, into I sigma is 0.175, that comes as 35 kP. So, what is that? So, 35 kPa is the stress just below point O prime, just below the corner of this loaded area, either below point O prime or below point E or below point B or below point D at some depth 2 meter. So, this is the stress or the pressure happening due to the application of 800 kilonewton load on this square area. Okay. Now, for the center, what is happening? Now, for the center, your modified B prime, that is modified B is 2 by 2 is 1 meter. So, center, when you are considering the center, at that time you are considering the small square, right. At the time, what is the magnitude of B? Modified B, that is nothing but B prime is half of that, 2 by 2 is equal to 1 meter. Similarly, L prime is also 2 by 2 is equal to 1 meter. So, therefore, your M is nothing but B prime by Z. Z is same 2 meter. So, 1 by 2, that comes as 0.5. Similarly, N equal to L prime by Z is equal to 0.5 meter, 0.5. Okay. Now, from table Now go back to the table. From table, I sigma equal to 0.084. Okay. So from this I can find out QV is equal to, pressure will be remaining same, into 4. So 4 times you have to multiply to get the total, because this is the pressure. If I do not multiply 4, then I will be getting the pressure due to this area only, but I have all the 4 areas, right. So I have to multiply with 4. So 4 into 0.084, that gives me 67 kg. Significant increase of pressure. That means you are getting higher pressure at the center than the corner, which is quite obvious, right. Now we will be taking the next example, next problem. Find the stress at point O of figure 2, say, if the loaded area is square with dg equal to dc equal to 4 meter for q naught equal to 400 kPa and depth z equal to 2 meter. Okay. Now let me show this area. This is the square area C, D, F, G, and the point is here. This is your point O, which is from D it is 1 meter on left side and 3 meter below. So this point is outside the loaded area, that is the interesting thing. Okay. This point is outside the loaded area. The loaded area is CDGF, this is your loaded area, okay, that is 4 meter by 4 meter, and on which you are having the pressure 400 kilopascal. Okay. And at depth 2 meter, you need to find out the stress at point O. Okay. Just below point O, you consider some depth 2 meter and you find out the stress due to the application of stress on this loaded area, because this point is outside the loaded area. Now how to do that? Okay. So how to do this? So you have to discretize this thing more, I mean very intelligently. Okay. So you will discretize this thing like this. This is the loaded area. So I am extending virtual extension. Okay. Some fictitious extension of this. I am extending this. I am extending this. I am extending this. Now I am giving the names like this. This is B, this is A, this is E, this is H. Okay. Now for point O, solution will be for point O. O has to be the corner, right, otherwise you cannot use this formula, that is Q V equal to Q naught into I sigma. That is only valid, that will only give you the stress at the corner of the rectangular area, right. So O has to be corner of some rectangular area, then only you can use that formula, you can take the help of that formula. Okay. So for point O, I can use OB FH, please look at this figure, OB FH, that means the whole rectangle, If I consider whole rectangle, O belongs to the corner of that rectangle, okay. So I can use that formula, minus OBCE, because actually that much loaded area is not there. What is the loaded area? CDGF. So therefore I need to deduct the dotted part. So what I am doing? I am doing OBCE, OBCE, that I am deducting, fine. So minus OBCE minus OAGH minus OAGH, but whatever we are considering, all the times O is coming as the corner. Please try to understand, please try to see the beauty of this problem, okay. So O is always coming as the corner. Now when I have considered OBCE and when I have considered OAGH and when I have deducted these two areas from OBFH, basically I am deducting this part twice. So therefore it has to be added, at least one part should be added, OADE. Okay. So if you do this operation, then you will be getting the stress at point O. Okay. So let us do that. For that we will be using some table that will be convenient for us, M which is nothing but B by Z, N which is nothing but L by Z, I sigma will be getting that thing from the table directly, and QV which is nothing but Q naught I sigma in KPSA. Okay. Now for OBFH, what is the value of M? For OBFH, what is the value of B and what is the value of L? The value of B is 5 meter, right. So B by Z will be 5 by 2 is equal to 2.5. How it is coming 5? 4, this is your 4 meter by 4 meter, 4 plus 1. So 5 meter is coming as B. And what is L? 7 by 2, 4 plus 3, right. So that comes as 3.5. So for that value of M equal to 2.5, N equal to 3.5, for that I will be getting I sigma equal to 0.243. So therefore this comes as Q naught I sigma is 97.2. What is Q naught? Q naught is given, that is 400 kPa, already it is given in the problem. Then coming to OBCE, for OBCE what is the value of B? OBCE, what is the value of B? That is the shortest dimension, that is 1 meter, 1 by 2 is coming as 0.5. And what is the value of N? 7 by 2, that is the longest dimension, 7 by 2 is your N value. Okay. So that gives me 0.137 as I sigma from the table, and ultimately this will be subtractive, it is coming as 54.8. Similarly OAGH, M will be 3 by 2, that is 1.5, and N will be 5 by 2, that is 2.5. Just check it from the figure with the same logic. This is also subtractive, 90.8, and finally OADE. OADE, what is your B? 1 by 2 will be your M, that is 0.5. What is the value of L? That is 3 by 2 is your N, and I sigma will come as 0.131, and that is additive. So summation of QV is equal to 4 kPa. Okay. So that means due to this loaded area at point O, okay, below the depth of 2 meter, you will be getting the stress as 4 kilopascal. Okay. So, in this way you can find out the stress if it is not even coming within the loaded area on. Okay. So, in that way you can find out the stress in anywhere, only thing is that you have to discretize the thing in more intelligent way. Okay. So, I will stop here today. So, in the next lecture we will be talking about we will be taking more numerical problems on the stress distribution. Thank you very much.